Okay, it's now time for the butterfly chromatography activity, which I've been teasing you with for quite a while now. It's really fun. I had a blast just doing the activity myself when I was preparing the slides for this presentation, and I can only imagine the excitement that kids are going to have whenever they're doing this, especially when they're doing it in the mindset of behaving like a scientist, where they're taking good measurements and classifying objects like scientists do. And also, they're going to be able to turn this science project, the results of it, into their decision process for making their art project, which is the butterfly with the filter paper that's left over. And so in this video, though, the goal is for me mainly to show you how to take an existing activity, something that's already out there, maybe even something you're already doing, and just by including particular activities where we are practicing our science process skills, how this can become a really fun, engaging science project. Okay, so let's start by talking about measuring a little bit more. And so I've created 5 points here to keep in mind and also to embed into the minds of your young scientists so that they will know how to make good measurements. So the first one is you need to define a marked reference point into your experiment whenever you're designing them. And then number 2 would be to use an instrument with a clear marking for 0. And I didn't write this, but students should also know where 0 is on the instrument that they're using. Okay, number 3 is know the unit system that you want to use ahead of time. And so this is for teachers also. Whenever you're planning an investigation where students are measuring, work it out ahead of time, because sometimes you'll want to turn your measurements into a graph or into a chart, or you'll want to use them in a math problem. And so knowing which unit system you need your measurement to be in for the math problem or for creating a graph that's scaled correctly, you want to make sure that your measurements are in the correct unit ahead of time. That would take a little bit of hassle out of doing the activity. And then number 4 is practice aligning your eyes with the object so that you avoid the effect of parallax and how that introduces error into your measurements. I mentioned that earlier. We're going to go over it again in this session because it is super important for measurement taking. Number 5, understand the certainty of your measurement. And so this is really important, I think, and something that we really maybe overlook at times whenever we're teaching kids how to measure. And so if we start making this a part of our measurement taking lessons, students will become really good at it. And so we'll just start with having a reference point. Remember back earlier in the class whenever I talked about the speed of the bubble lab. And so in this particular lab, we needed a reference point to know when to start and stop our timer so that we could take our measurements correctly for the lab. And so would that be at the top of the bubble? Would that be somewhere in the middle of the bubble? Would that be at the bottom edge of the bubble? Probably either the top or the bottom edge is going to be a lot easier for students to know exactly when it reaches a particular point, and easier reference point to make lines with to draw measurements. And so having a good reference point is good in the design of your experiment. Now, the second thing was always knowing exactly where 0 is on the instrument you're using to measure. And that's often the case with rulers. Sometimes rulers will have this edge over here to show the number 0, but there are actually no markings there that students will use. And so students will oftentimes mistake the edge of the ruler as the 0, and it will offset their readings tremendously whenever they're taking their measurements. And so that's something super important to address with students that they also need to pay attention with every time they pick up something to make a measurement. All right, parallax. We looked at it earlier in the scientific process class. Here it is again. Notice that whenever my eyes align and are looking at the object at an angle, how it shifts what it looks like the instrument's marking is actually on. And so if we look to the left, our screwdriver will look like it's a little bit shorter. But if I'm looking at it from the right, it'll appear like my screwdriver is a little bit longer and line up with this marking here. Whereas if we get directly over top of and align our eyes with the edge of that and the ruler, we get a more accurate measurement. So students need to understand that parallax causes error. right? And so just remind them every time they're taking measurements to think about parallax. Okay, now for the most important thing on my list, which is the certainty of the measurement. And so certainty is the confidence that you have in the measurement that you're reporting. So how for sure are you that it's what you're saying? And so that often depends on the number of significant digits that we report, and that's determined by the instrument that we're using and how it's marked. And so the scientific protocol for taking a really good measurement, an accurate measurement, is estimating only one place value beyond the marking of the instrument when you report your measurement. And so again, ignore over here where I accidentally didn't line my ruler up correctly. Just block that out and focus on this end of the ruler, just for the sake of teaching you guys what I mean by the certainty of a measurement. And so this ruler is marked, and the largest marking on this side is just in whole centimeters. We go from 0 to 1 to 2 to 3 to 4 to 5. And so I know with complete certainty that from my reference point to the edge of my filter paper, that I am for certain that it's at least 5 centimeters long. And so I'm going to start by writing down 5 and then a decimal point. There's my ones place value. And then the next marking that we can move down to are these tenths of a centimeter. And I know it's tenths because I count it, and there are 10 lines between each centimeter, or that's also a millimeter. And so I'm going to count these as 0.1, 0.2, 0.3, then 0.4, 0.5 is the larger line, and it's followed by 0.6, 7, 8, 0.9, and then we just go straight to the next whole centimeter after that point. And so looking at the edge of my filter paper, I'm thinking, well, it's not quite at that line, but it's pretty close. And so I have to put 5.0, because it hasn't quite reached the 10th. But now I need to estimate one place value beyond that marking. And so there are no other small markings on this instrument. And so it's time to do that. And so I'm going to estimate to the 100th place value. Now, I'm looking, and the edge of that filter paper is almost touching the 10th mark. And so for my measurement, I'm going to record 5.09 centimeters. Now, this is a great measurement because it puts the mindset of certainty in the reporting of it. Now, it doesn't have to be completely accurate. It may be 5.08, it may be 5.07, but it has enough information here to explain to another scientist that it's almost 5.1, but it's not quite 5.1 centimeters. So that's a good measurement. And scientists know that this 9 is the least certain digit because it's the 100th place value, and this was the one that we estimated. And they're aware of that. Now, what it is bad to do whenever you're reporting measurements is just to round up to 5.1, because this would tell a scientist that you're only certain that your marking is close to 5 centimeters, not that it's actually close to 5.1, because they are going to round the last digit, because they're going to assume that the last digit is the least certain. So this 5.0 and 5.1 are two completely different measurements, whereas 5.09 actually tells us more precisely, or with more certainty, not precisely, but with more certainty what our measurement is. And so when students get the idea that, oh, we need to estimate one place value beyond, they might start doing too many place values beyond, because they'll see a significance in reporting that, but they won't see the significance in only reporting that estimation, right? When I add place value, I'm telling somebody that I used an instrument that had better markings on it than my centimeter and tenth of a centimeter. So I'm telling them I have a more exact or a more certain measurement than what I actually have. And so that's actually something you do not want to do unless you have an instrument capable of measuring to that place value. And so a good measurement could be 5.08, like I said, or 5.07. These measurements are reported to the correct place value based upon the instrument that I'm using. So getting students to practice how to take those measurements depending on the instrument they're using are super important. Think about for a minute a glass beaker compared to a graduated cylinder. The markings on a glass beaker are more sporadic, right? They're only in 25, 50 milliliters, 100 milliliters. Those are spread out markings, whereas a graduated cylinder could be marked per milliliter and also per tenth of milliliter. So one instrument can measure volume with more certainty than the other. So think about when you're designing experiments, what instrument you want your students using to do their measurement, and how do they correctly report to what place value using that instrument. Okay, I've held you up long enough. Now that we're done talking about those 5 points of good measurements, we're going to take a look now at the video itself of the chromatography butterflies. Wow, is that not just cute and looks like a lot of fun? I could do that all summer, actually. I think I'd have a blast with it. I also want you to know, though, that there are a lot of other crafts that you can do with the results of your chromatography coffee filter papers. You don't have to just make butterflies. I've seen some videos where they were turning them into dancers, and so the coffee filter was like the dress on the dancer. And so I'm sure there are plenty of things you can do, so check them out. I just wanted to show you guys that one in particular. Okay, so now let's talk a little bit about what chromatography is. We saw it in action in that video, but it didn't really explain what it is. And so chromatography is the separation of molecules due to different properties that they have and how they move through a solvent whenever the solvent is moving through, like the filter paper, for example. And so those different rates of movement are caused by the molecules' properties and how those molecules interact with the properties of the solvent that you're using. So in that video, the solvent they used was water. And so water is a combination of oxygen and hydrogen that are chemically bonded together. And so oxygen has 6 electrons, valence electrons, that are available for bonding, whereas hydrogen has 1. And so hydrogen will bond or share that 1 electron with oxygen to give it a full octet of electrons in its valence shell. So that's how the bond forms. But in consequence, oxygen is got an abundance of these electrons orbiting around it, whereas hydrogen has very few compared to it. And so that causes the oxygen end of this molecule to build up a slightly negative charge, and in response, the other side of the molecule becomes slightly positive. And so we say that these are like north and south poles, or negative and positive poles of the molecule. And so we say that they're polar molecules. And so a polar solvent will actually be attracted to many other things, right? Because of these poles that it has. And so even water itself will want a hydrogen bond with another water molecule because of the attraction between the positive and negative ends of the molecule. So this property here of attraction is we see in surface tension, we see with adhesion and cohesion as well. And so capillary action also works because these solvents will work their way up through a solid due to these forces of attraction as a result of their polar properties. Okay, now water is not the only solvent that you have to use. In fact, you can create an investigation where you test just different solvents with same types of markers. And so isopropanol, which is rubbing alcohol, acetone, which is fingernail polish remover, are also polar solvents. You'll notice the red oxygen atom is on one end of the molecule. That builds up a negative charge or a negative pole. And then the rest of the molecule is slightly more positive than it. Now, these molecules are a little bit bigger than the water molecule, but they will still respond to the same way. And so in chemistry, there is this saying called like dissolves like. And this is very true in terms of chromatography. Whenever molecules are similar to the solvent, they're going to dissolve into it, and they're going to move up through the filter paper with the solvent as the solvent moves up through with capillary action. But those molecules are going to eventually fade out of the solvent. They're a little bit heavier, maybe. They have a little bit more mass. They can't stay as attracted to some molecules as they're moving, and so they just slowly lose that effective attractive force that they have on one another. And this causes that bleeding effect that we see when we saw that chromatography demonstration in that last video. So sometimes you'll have something where the ink dot that you made doesn't move, and that's because it didn't dissolve in to that solvent due to those molecular properties. Okay, so let's set up for the science investigation. Maybe you want to test different solvents, or maybe you just want to test different markers with the same solvent, whatever. But I do want to give you some safety warnings about the solvents that I've mentioned in this video. Rubbing alcohol and fingernail polish remover are both very flammable, so don't have any fire sources, candles, anything like that around while you're doing this experiment. Also, acetone dissolves plastic. It reacts with it. And so if you use a plastic cup like the one I'm showing you here for the alcohol in the water, it will actually eat a hole through the bottom of it, and then the acetone will start coming out of the bottom, and then you'll have a mess on your hands. And then chemicals that students would likely be touching because they're not in a container. And so make sure you get like a glass beaker or something whenever you're choosing to use acetone. Also, keep in mind that both alcohol and acetone look just like water, and so they are actually very harmful if you ingest them. So be very direct with your students and let them know that it's not okay to drink any of these. Even though they look like water, they are not at all like water in terms of how they respond to the human body. And then you also want to wear safety glasses because these things could splash, and you don't want them getting in the eyes of your students either. Now, volatile, I think I skipped that on accident. Volatile means that it evaporates quickly, and so acetone will do that. And so it will leave the liquid phase and enter the gas phase readily. And what that means is if you use too little acetone, it will disappear, and then it won't work. It won't actually touch the strip whenever you put it in. And then also, if you use too much of it, you could fill your room with these vapors of acetone, and that could also be harmful for students. So if you're going to use a lot of acetone, you want to make sure that your room is well ventilated. You're cycling air from outside of the room and pushing the air from inside of your room, outside of the building in particular would be best. Okay, here's some key terms. I've been using them, but here are their definitions. Solvent, that's the substance that does the dissolving. So our solvents are water, alcohol, and acetone, or you can even use salt water. Salt water is different than the other three because it's composed of sodium chloride, which break down into ions when they're dissolved in water. And so you actually have ion-ion interactions or ion-dipole interactions. And so you'll get a different result to your markers than you would if you use these polar solvents. A solute is the substance that's being dissolved. So in our case, it's the colored pigments in the markers. And what is chromatography used for? It's not just used for fun crafts like this. we can actually learn a lot about a substance by performing chromatography on it, because it separates it out into its components, and so then we can see what it's made up of. And so in particular, we would do this in a science field whenever we are identifying and correlating the components of blood at a crime scene, and that can actually help investigators take a suspect and use this evidence of their blood and confirm that they were there at the scene of the crime. Creating vaccines is another use for chromatography, and also testing how good a Coca-Cola tastes or some other beverage is done by using chromatography, right? It helps us figure out the different proportions of chemicals within a mixture. Okay, so where does the classifying come in? Well, I'm actually going to start this activity out by classifying. I'm choosing to do different markers with particular solvents to see which ones respond and which ones don't. And so I'm going to start by grouping my markers into groups, whatever groups that the kids want. They can group them by color. They can group them by brand. They can group them by length or width. They can group them by the type of marker, whether they're permanent, washable, or highlighters. Doesn't matter. As long as they just choose one grouping style. So in this little clip where I'm doing the activity, I'm grouping by color. Over here's a photo of where I actually group by brands. So I had a particular brand of highlighters, some dry erase markers. I've got the brand Imagine, which had these really thick markers, but also these really thin markers. And then I had Crayola, thin and thick markers. I had permanent markers, and I had Sharpie permanent markers also. And so you can use your classification to decide what you want to test. And so have students pick a few markers from their groups, or do all of one from each group that they made as well, is another way you can do it. And so use this, though, as an opportunity to instruct controlling variables, right? And so we talked about that integrated science process skill of controlling variables. What's our independent variable going to be? And only select one. Is it going to be the marker colors, the different colors, like using red, black, and blue instead of using different brands? Using the same brand but different colors of it? Or are you going to change the brand of marker? Are you going to use all black markers but use a black marker from each group? Are you going to change the type of marker that you use? So I want to use a highlighter. I want to use a washable marker. I want to use a permanent marker. I want to use a dry erase marker. Could be the independent variable. Or do I want to test the different lengths? Maybe I want the small marker, the large marker, and then the largest marker. However the kids decide what they want to test, let them do. And I encourage them to do different ones. That way you can have them share the results of what they've done with each other in the class, and that will help them brainstorm, well, which markers do I actually want to use when I'm making my butterfly? Okay, so I mentioned controlled variables. Remember to use all the controlled variables to make your scientific investigation something that you can actually produce results with and write a conclusion about what happened. And so length of the filter paper is something you want to control. So in the images here, I just cut out random lengths. It doesn't really matter. You can have any length you want as long as you just put it in the cup so that it just gets a tip of it touching the solvent that's inside. You don't want a whole bunch of stuff dangling down, because then your colors are not going to slowly be dissolved by the solvent, and so they won't actually spread out whenever that happens. Also, you want to make sure that the amount of solvent that you use is identical in each cup when you're going to do this, and the distance for your reference line, so where your ink dot starts at, you want to draw that the same distance away from the edge every time. And the amount of time that you allow to pass before you take your measurements, you want to keep that consistent. And so it could vary depending on the length of your filter paper, and also how much time you have available for a class. Of course, You don't want it to go too long. You don't want it to go too short, because then your colors won't spread out really well, or your colors will spread out too well and you won't be able to analyze them. And so I would definitely practice this before you do it with the students, to try to figure out, well, how long do I want this to actually move through the filter paper before we stop and take measurements. And then the dependent variable. What is it that we're going to measure? Well, you'll notice just by these images, you can get a lot of different consequences depending on what markers you use and which solvents you use. And so you're going to have to maybe explore around with what it is that you're going to do, or what your kids are going to do, and then help them figure out what their dependent variable is after they actually have the results, rather than building it into their procedure. This may be an example where you're doing a journal and then that comes up at that point in the process, rather than them planning the experiment out themselves. And so you could measure how far the dot moves from that reference line. You also can measure how far the solvent moves. Notice in this image that the dot and the solvent do not move the same distance. You can measure the number of colors that appear after they separate. This one appears to have 3 colors. You can choose to measure the RF value, which is the ratio of the solvent movement to the solvent front. Okay, so there's a lot of variations to how you can do this. And so my video just covers me doing a couple of examples from each. And so we're going to watch my video now.
We're going to start by cutting our filter paper into different chromatography strips so that you can have one for each experiment. The size of your strip depends on which cup you're going to use. You want the filter paper to just touch the top of the solvent at the bottom of the container. Then tape the top of the strip to the straw so that it can dangle into the container. Now let's make a reference point on our strip using a pencil. The graphite in the pencil is not very likely to disappear due to the solvents that we're using. The reference point needs to be about 3 to 5 centimeters from the bottom of the strip. This is where we're going to put our ink dot on to mark its starting point. Just about ready to go. Pour some of your solvent into the bottom of the container, and then carefully place your straw across the top of the container so that the chromatography strip will just touch the top of the solvent and start absorbing into it. Due to capillary action, the solvent will rise up through the filter paper and will interact with the ink along the way. For the orange ink, I've used alcohol as the solvent. For the purple ink, I've just used water. A good ways into the experiment, I decided it was time to stop, and so I carefully removed each strip and set them on a paper plate, and then I marked where the solvent front was. That's where the solvent stopped in the experiment. I also went to measure how far the ink moved off the initial reference line. For this purple one, nothing seemed to happen. I wonder what would happen if I put it in the alcohol solvent. So I made a whole new strip to test it out. Well, this time it seems to be working. At least the solvent is interacting with the ink this time. Instead of testing the solvent type this time, let's try different brands of markers. I'll put a black dot for each brand of marker on the same strip and put them in the alcohol solution. Let's see what happens. The experiment is still going on, but it looks like the permanent Sharpie marker is turning purple and spreading out, and the dry erase marker is doing nothing. Or maybe it's moving just a little bit. I also tried out this green magic marker. Wow, look at these colors. There are 3 different colors. The blue seems to travel the furthest, then the green, and then the yellow travels the least. Okay, I'm going to give it a try at a design, and so I'm going to poke a hole in the middle of my filter paper and make a wick with another sheet of filter paper. That way I can just carefully put the wick into the solution so that the colors will slowly spread out evenly. This is a lot trickier than it looks. Okay, while that's going on, I'm going to try a whole new experiment. I'm going to mark 5 centimeters from the bottom of my filter paper and then draw a new reference line all the way across along that point. And so I've already grouped different markers into different categories, and I want to test each of them and compare them within the type of marker that they are. And so I've folded up the filter paper and put it in the bottom of the container so that the solvent can come up through it. And well, this is what I got. Although it's not the best result, it does help me compare the different colors of a similar type of marker. What ideas can you come up with?
Okay, so classifying. Return your class to the topic after they have the results of classifying, because they'll see that some markers might actually have had results that surprised them. And so now they can classify their markers based upon the results of their experiment. And so we can classify them by the number of colors that appeared. We can classify them by which ones responded to solvent A, which ones responded to solvent B, which ones responded to solvent C. And in that classification system, we could even have more than one marker in the same group. We can even have some markers that didn't respond at all. And then which one travels the furthest? Which one traveled the least? Okay, so we're going to talk about the RF ratio a little bit. Maybe you'll want to calculate this. This is a calculation that's used especially whenever there's more than one substance in a chromatography mixture that is spread out. And so we measure the amount that each separate substance travels, and we report that with the RF value. And so first we're going to measure the distance that the molecules moved in the solute. So here I got a good measurement of 1.44 centimeters. And so that was done again with using my mindset of certainty with this ruler. I put my reference line at 0, as close as I could to 0. And then I drew a line from the center of the dot where its new position was. And then I came over and I knew that it was after 1, and I counted 1, 2, 3, 4. It was after the 4th little marking, which is 4/10, but it wasn't quite at the half centimeter mark, or 0.5 centimeters. And so I'm going to have to estimate the hundredths place value here between the 4 and the 5. And I had a hard time doing this. I felt like my line that I drew was in the middle of the space that was there. So it was either going to be 1.45 centimeters or 1.44 centimeters. And after careful consideration, I went with 1.44 centimeters. So the solvent front, you're going to measure the same way, just from make sure you mark your solvent front before it dries so that you'll have it. And then here, the purple dot, it had a distance of 1.56 centimeters. And so if I get the RF value for this particular dot, I'm going to do 1.56 centimeters, the solute, divided by 3.20 centimeters, the solvent, and then the solvent always goes in the denominator because that's the whole part of this fraction, right? That's the furthest the dot possibly could have traveled. It can't travel beyond the solvent, so that's why that has to go to the bottom in our RF denominator. And so if we simplify this fraction by using division of the decimals, we get 0.049. without units. The centimeters cancel. And so that's the RF value. So it traveled half the ability of the solvent, basically, is what that tells us. Okay. Wow. So you guys have seen the measuring and the classification components of the chromatography experiment. You've seen the art activity that you can use following the results that you get from doing the chromatography experiment. And so now I want you guys to reflect. Think about your book that you guys identified in post number 4 yesterday or in day number 1's class. And what science process skills do you think you could teach in an activity relating to the topic of that book? Think of an activity or even a craft that maybe you do, and what measuring can you do for that activity? What classifying can you do? What other science process skills that we haven't talked about in this video, like observations, inferences, or any of the other ones that we addressed, making predictions, could you actually use while you're doing activities with that book? And then the second thing for this journal, number 6, what activity could you do to help students practice their skill in addition to what you may already be teaching? So how could they get better at it? Could you do a direct instruction of it somehow before you actually do it in the activity? All right, so I hope that you guys at least try that out and decide if you're going to do it with kids. It's a lot of fun. Let me know if you have questions or want suggestions for improvement. I know I presented a lot of different variations in this lesson instead of just showing you one particular way, and I left it a little bit open for you to try things. So, but please let me know if you need help along the way while you're doing that. All right, I will see you guys next class.